I'm Dave Brown for Teletrain, and today we'll be examining a few more pneumatic components and then showing how they can be used in some basic circuits here in Lesson 10 of Parker Hannafin's course, Industrial Pneumatic Technology. It is entitled Regulators, Excess Flow Valves, Boosters, and Sequence Valves. Let's begin by defining a new term. It's sequence valve. And as you'll see, its name simply refers to the job it does. Here's a circuit that makes use of a sequence valve, here. We're supplying air to two cylinders, making them actuate one after the other, or in sequence, by making them actuate at different pressures. This is a simplified schematic of a basic circuit that might be used in a clamping and forming application. In this case, we have set the sequence valve here to 50 psi. We have sized the clamping cylinder so that it will operate at a pressure of less than 50 psi. In this position, the directional control valve passes air to the clamping cylinder here, and it begins to move. But no air can pass to the forming cylinder until the air pressure has reached 50 psi, which won't happen until the clamping cylinder has completed its stroke and clamped the work in place. When 50 psi is reached, this valve opens and air is allowed to pass from the inlet to the outlet, and the forming cylinder is activated. So by using a sequence valve, we are able to control the order in which cylinders are activated. For safety's sake, let me mention that this was a simplified circuit for purposes of illustration. In real life, there would be additional components to make sure the clamping cylinder had completed its action before the forming cylinder moved. The sequence valve we used in this particular circuit is a device you may remember from Lesson 4. It's called a pressure regulator. It is normally used to reduce air pressure going to an actuator or circuit down to a certain preset value, and thus save air usage. It also helps keep system air pressure constant, regardless of changes in upstream pressure. This housing here is called the valve body. It is normally cast from some metal like bronze or zinc. This is the primary or inlet port, and it gets connected to the upstream or supply side of the system. The secondary port, here, supplies air at a constant pressure to the downstream side. This is the adjustment knob here, and it is used to set the output pressure of the valve to the desired level. This regulator has a smaller capacity and is most often used for compact control cabinets and miniaturized circuits. It has what is called a non-rising adjusting knob. Here you can see the internal parts of the regulator. The primary port here, and this passage through the valve body that leads to the outlet. Flow through the valve is interrupted by this poppet here. This rod connects the poppet to this piston. So when the piston moves up or down, so will the poppet. The regulator is operated by air and spring pressure. This passage here allows downstream pressure to back up into this chamber, and it develops a force on the underside of the piston. This force works against the spring here, and when the air pressure is high enough, the piston moves upward, and the poppet begins to shut off airflow. When the preset downstream pressure is reached, the piston will be high enough to allow the poppet to seat fully, shutting off the flow completely. By adjusting the tension on the spring, we can control the downstream pressure at which the valve will close. In this way, a relatively constant pressure will be applied to any actuators connected to the valve outlet. Here is the symbol used to represent the pressure regulator we have just discussed. The arrow indicates the direction of air flow through the valve. Here is the adjustable spring. And this dotted line leading from the output back to the valve tells us that the valve is operated by secondary pressure. Many times a regulator is used on what is known as a dead-end system. This means it serves only one leg of a circuit, which may not have continuous use. In this case, with the regulator we have just discussed, there is a possibility of a pressure buildup on the secondary side of the circuit. This can be caused by leakage past the regulator, thermal expansion, or a load pushing externally against the cylinder piston. We can get around this problem with what is called a venting type regulator. Here's what it looks like. And you have to look closely to see what the difference is. It's the small vent hole here that's been drilled into the piston chamber here on the end near the adjusting knob. This illustration shows the complete venting path. In addition to the venting hole through the valve body here, you can see that the piston rod is not connected to the piston. Instead, the end of the rod is slightly tapered, so it will seat against and seal another vent hole that has been drilled in the piston here. Here's a piston we've removed from a venting type regulator, and you can see the vent hole here. The end of the piston rod is tapered. So if we put the two surfaces together, we get a tight seal. You may be asking, okay, if the piston and the poppet aren't connected by the rod, what makes the piston move? Well, let's take a look at that illustration again. You can see down here, there's a bias spring around the poppet. The force of this spring tends to push up on the poppet, causing it to seat. You can see the spring fits right around the poppet. The spring isn't very big, but it will develop enough pressure to force the poppet closed. Here is how the rod and piston fit together when the regulator is regulating. Secondary pressure working against the piston here causes it to move up. The bias spring around the poppet pushes it upward, reducing the primary to secondary flow path as necessary in order to keep a constant pressure at the output. Under these conditions, the rod is sealing off the vent hole in the piston. Okay, so what happens if the secondary pressure goes up to a pressure higher than the valve setting? As we've said, this might be caused by a thermal expansion of air or a big external load pushing against a cylinder piston. Well, the extreme secondary pressure would continue to push the piston in an upward direction. Because of the spring, the rod and poppet follow it upward. But look what happens to the poppet. It seats, fully shutting off air from the supply, so pressure cannot continue to build from the inlet. But the rod, since it is fully extended, cannot close the hole in the piston. So the increased secondary pressure is allowed to vent through this hole and the hole in the valve body, reducing pressure in the secondary side. When the secondary pressure decreases, the spring forces the piston downward, and the vent hole is again sealed by the rod. Under these conditions, the valve begins to regulate normally again. Instead of a piston, some venting type regulators use a diaphragm like this. It is usually made from a combination of fabric and rubber, so it is very strong, yet is soft and flexible. It has a small venting hole in the center, here, and the edges flex, so the center of the diaphragm can move up and down easily. In order to replace a damaged diaphragm, you simply take out these screws here and the valve bonnet. This part here comes right off. Remove the damaged diaphragm, replace it with a new one, and then just screw it back together. In some applications, it may be necessary to readjust the air pressure from a remote location, say from a main control panel. One way this is done is with what's called a pilot-controlled regulator. This is a pilot-controlled regulator. You can see it has a slightly different shape, and instead of an adjusting knob, we have this pilot port here, where the pilot supply line would be connected. Here is the input port, and this is the output. This small arrow cast into the side of the valve body indicates the correct direction for airflow. A pilot-controlled regulator operates in the same basic way as an ordinary regulator. The difference is that the secondary pressure on the piston works against the pilot air pressure rather than a spring. As the pressure on the outlet side of the regulator rises, it goes through this hole here and pushes upward on the piston. When the force on the piston caused by the secondary pressure in the line is greater than the downward force caused by the pilot pressure, the piston and poppet move upward, and the poppet reduces flow through the valve, and the output pressure is maintained. When the secondary pressure drops below the desired value, the piston and poppet move downward, allowing more flow through the valve. Some regulators, like this diaphragm unit, combine the venting feature with pilot operation. You can see it uses two diaphragms. The vent hole is here in the center. Air from the supply side comes in this port here, through this passage to the outlet. The poppet is spring biased, and the rod is not attached to the diaphragm. When the valve is regulating, the force of the pilot pressure on the diaphragm pushes it downward against the rod, sealing off the vent hole and preventing the poppet from closing off the air passage here. If the force of the secondary pressure exceeds that caused by the pilot pressure, there is a larger force on the bottom of the diaphragm than on the top, so it flexes upward, as you see here. The bias spring seats the poppet, closing off the supply. The downstream pressure vents through the hole in the diaphragm here and flows between the two diaphragms and exits the valve through this hole here. When excessive secondary pressure has been relieved, the diaphragm returns to the normal regulating position. In all pressure regulators, as the flow is increased, the pressure on the secondary, or what is called the reduced pressure side, drops slightly below the no-flow pressure setting. This difference between no-flow pressure and actual operating pressure is called regulator droop. For this reason, designers should select a regulator that has minimum droop in the normal operating range of a system. Do you remember what we said the usual functions of a regulator are? Well, there are two. First, it is intended to pass air at a constant output pressure regardless of changes in supply pressure. The second is to reduce the air pressure to a level that just meets the necessary work requirements, so we don't waste pressurized air. Let's take a look at a circuit that uses two cylinders. It is similar to the one we saw earlier in the program, but this time we have a different requirement. We want to operate both of these cylinders off the same supply, but the one doing the clamping can do its job with a much lower pressure than the cylinder that's doing the crimping. It's an ideal situation for a couple of pressure regulators. Closest to the air supply is the main pressure regulator, which supplies air to the cylinder that does the actual press operation. Then here is a secondary regulator that supplies the actuator doing the clamping. We adjust it to a much lower pressure, just enough to allow the actuator to develop the required clamping force. The four-way directional control valves are manually controlled by the operator to deliver air to first the clamping actuator and then the press operation. So in this case, we have used two regulators to reduce the pressure to two different parts of a circuit. Each cylinder gets just the pressure required to do the job. Suppose we had a requirement for the cylinder to perform work during both strokes and exert one force when it extends and a different force when it retracts. What's required in this case is a dual pressure circuit. This one uses a 5-ported, 4-way directional control valve here and two pressure regulators. We will set this one to deliver the right pressure for extension, and this one will adjust to give us the required pressure for retraction. Here is the cylinder we want to control, and our supply comes in right here and is connected to both regulators. We have set the circuit up so you can see how it actually works. Here are the pressure regulators, and we've set them to deliver two different pressures. Here's the 4-way directional control valve, and here's the cylinder. We'll use this scale to measure the approximate force in both directions. Okay, when we move the control valve and pressurize the rod end of the cylinder, we get a force of about 15 pounds. Now we swing the scale around like this and move the control valve to pressurize the cap end. The cylinder extends. As you can see, the force is now about 25 pounds. You can better understand what's happening by looking at the circuit diagram again. The directional control valve is positioned so the cylinder rod will retract. Supply pressure comes in here, flows through this regulator, through the control valve, and into the rod end of the cylinder, causing it to retract. If we move the directional control valve into the position shown here, supply pressure is now routed through this regulator, which is set for a higher pressure than the other one. Then on through the valve and into the cap end of the cylinder, causing it to extend. Okay, so by using a 5-ported 4-way directional control valve and setting different pressures on two regulators, we can provide different forces during extension and retraction and make the cylinder's operation more efficient. Now here's another problem. Suppose the plant just got in a new piece of production equipment, like a press or a punch, and you find that the pressure it needs for a part of its cycle is higher than your plant's air supply pressure. What do? Well, if the volume of air you need is not too large, you might use something we looked at way back in Lesson 1. It's called a booster or intensifier. Let's review how it works. Air is supplied at low pressure here to extend this booster piston, which is connected to this smaller piston called the high-pressure ram. As the ram moves, it compresses the air in this part of the intensifier, raising its pressure. How much of an increase in pressure will we get? Well, that depends on the ratio between the areas of the large and small pistons. In a 5-to-1 intensifier, for example, the large piston has 5 times as much area as the ram, and the pressure at the output will be 5 times the pressure at the input. But we don't get this pressure increase for nothing. Remember our formula, P1 times V1 equals P2 times V2? It tells us that as the pressure of a gas increases, when its temperature is held constant, its volume will decrease. In our 5-to-1 intensifier, we get our pressure increase because the volume on the input side is 5 times the volume here on the output side. So if we are raising air at, say, 100 psi to a pressure of 500 psi, our system will have to use 5 cubic feet of air for every cubic foot we get at the higher pressure. We are trading volume for pressure. Here's an interesting 2-to-1 booster, which at least one manufacturer markets. As you can see, it uses 2 pistons that are the same size. But by allowing primary air pressure to the top side of both pistons and venting this chamber, they are able to get a 2-to-1 pressure increase in this chamber. Why? Because the combined piston areas here and here on the primary side are double the area here on the output side. On the return stroke, the flow paths are reversed. Primary pressure is applied to the bottom of both pistons, and this area becomes the high-pressure chamber. Now let's look at a circuit that uses an air-to-air booster. This is what is called a demand circuit. That is, the booster functions only when it is necessary to bring the receiver pressure here up to the desired value. This 5-ported 4-way directional control valve is pilot-controlled by these 2-way cam-operated valves here and here. When pressure is applied, the cylinder will cycle back and forth, its direction changed by the cam-operated valves that are actually working as limit switches. The final output pressure will be a multiple of whatever input pressure we set on this regulator right here. When the pressure in the receiver has built up and the forces on the input and output side of the pistons have reached a balance, the booster stops, and it won't restart until the receiver pressure drops. Okay, 2 more things before we leave boosters. First, the fluid in the output side of a booster doesn't have to be air. Sometimes oil is used in what is called an air-to-oil system. It operates on the same principles as an air-to-air system, and your text provides some examples of particular circuits. Second, a safety precaution. You should always have a pressure relief valve on the high-pressure side of a booster to be sure that the pressure is not intensified to a dangerous level. Now let's talk about another safety device. This operator is performing a task that's done in many manufacturing plants across the country. He's using compressed air for cleaning. Here's what could happen if a hose broke and the airflow wasn't stopped. It's called whipping. To help prevent this from happening, the OSHA regulations require all hose systems larger than 1/2 inch to be equipped with a safety device that will reduce pressure in the event a hose or fitting should fail. The valves used to do this are called air fuses, or excess flow valves. Here is an excess flow valve. This is the input or supply side here, and here is the output side. The valve is normally passing and closes when the flow rate suddenly increases past a certain value, as would happen if a line breaks. This illustration shows one design. Flow is through the valve from left to right. This poppet here is held in the open position by this spring, and you can see air can pass through this passage here in the poppet. If the outlet pressure in the line were to decrease, as might happen if the line were to break, the surge of air from the supply would drive the poppet to its non-passing position, as you see here. The air will remain shut off until the break is repaired. An excess flow valve is required for each length of hose of 100 feet or less. For hose runs over 100 feet, you should install another valve every 100 feet. The valve should be mounted off the tank, and this manifold assembly is a common way of meeting valve installation requirements. This concludes Lesson 10. The lesson review and exercises begin on page 127 of your text. I'm Dave Brown for Teletrain.